Hello, everyone. My name is Kaiming Cheng from the University of Washington. Today, it's my great pleasure to kick off this AR/VR session and introduce you to our work. When the user is inside a user interface, an empirical study of UI security properties in augmented reality. The idea of augmented reality can be traced back to the 1960s. Over the past few years, we have seen great improvements in the AR hardware as major stakeholders such as Apple, Meta, and Microsoft all release their AR devices. In addition to the hardware advancement, we also witness significant growth in the platforms that support AR technologies. Each type of AR device now comes with its own SDK, which are designed to facilitate third-party developers to create this immersive AR experience. It is a very exciting technology to work on these days, but this landscape also raised practical questions, which is, what are the different design choices made by these platforms, and what are their security implications? And just like how past research examines different browsers or IoT device, for this paper, our goal is to provide a fundamental systematic evaluation of these current AR platforms. For this work, as the title suggests, we choose to focus on the AR UI security. So what is AR UI security? Well, compared with the two-dimensional UI that renders on a flat screen, AR UI places virtual content in a user's perceptions of the real-world environment. To provide a more concrete example, let's look at the simple AR app that can help you vacuum the space. So basically this app can help you make sure that you don't miss a spot when you vacuum in your home environment. Pretty cool, right? What I like about this app is it also illustrates three key elements of AR UI, which is the user perception of the physical world, the virtual content get rendered on the real world, and user interaction with this virtual content. So if we put this AR UI under the lens of threat modeling, we found that recent work has already begun to study the UI-related security and privacy issue targeting on the first layer. For example, just last year, we have 3 USENIX papers investing various attacks on this layer, including inferring information of the real-world environment, inferring bystander in the real-world environment, and obscuring real-world important content. So in this work, we consider a threat model where we have multiple principles interacting with AR UI. One example could be a third-party embedded code that's running in an AR application. The attack goal for the third-party code is to interfere with other principles AR content or interfere with their interactions with the AR content. So in this paper, we explore 5 different UI attacks, and clickjacking is one of them. So let me walk you through. So suppose you have a malicious third-party application that is trying to maximize its ad revenue. So it's trying to trick user into clicking the ads as much as possible. So on the left, you can see this dummy red advertisement created by a benign ad library. On the right, you see this enticing blue box saying, "Click me to win a free cookie." So while this blue box is visible to user, when users trying to interact with this blue box, their interaction actually goes into the red box, which is a demonstration of the clickjacking attack. And we implement this proof of concept attack on Apple's ARKit, which because of the way ARKit implement their systems. So while this proof of concept attack succeed on ARKit, we are more interested in the underlying property behavior that makes this attack possible. So the clickjacking attack is possible because it's exploiting a property we define as same space. So what is same space? Suppose you have 2 virtual objects that get rendered into the same 3D spatial coordinate. Which one gets rendered on top? Which one receives user input? Depending on how different platforms implement with these corner cases, if the object is visible, but it is not the same one that gets user input, it enables potential clickjacking attack. So how do different AR platforms handle these edge cases? To perform a systematic evaluation on different AR platforms, we propose specific evaluation metrics to study the same space property. The metrics we propose investigate which objects are visible, which objects receive user input, is the rendering consistent or flicker, is rendering order consistent, is the interaction order consistent, and finally, are the objects that are visible is the same objects that receives user input. So the way we evaluate these AR platforms' behavior on this given property is through a systematic evaluation. We implement these test cases using native API and run it on the designated AR devices. We open source our code to facilitate future research. We also implement a role-based component to represent executions from different entities, principles. We then use a central state machine to coordinate this event-driven test steps to avoid any racing conditions. And finally, we structure our code to support future extensions to other or future AR platforms. So after developing this test case, we run about over 100 trials on each property to account for potential non-determinism. So we first run each test cases 5 times. We then run the same test at different spatial location. And eventually we make the full test and run it for 5 times. We did found that, for say, the results for same space on Oculus is different depending on where user initiates interaction. And it is the result due to the 3D spatial nature of augmented reality systems. So recall the clickjacking attack we just demonstrated. We identified 2 key metrics that map to this attack, which is interaction consistency and rendering interaction inconsistency. So after examining these metrics across all platforms, we can start to see the different design choices made by these AR platforms. And from there, we found that this attack is possible on Google's ARCore, Apple's ARKit, Microsoft HoloLens, based on our property evaluation. The second property we looked at is invisibility, where we investigate the ways AR platforms can create transparent objects and whether such transparent objects can register user input. So if you have an invisible object that absorbs user input, you can then create what we call a denial of service attack that basically surrounded the target objects and block user from interacting with it. We run a throughout investigation on all platforms, and we found that all platforms are vulnerable to this attack under different setup conditions. The third property we look at is synthetic input, which we investigate whether AR platforms can separate user input from synthetic generated input. We found that all platforms lack mechanisms for input provenance, which makes them all vulnerable to input forgery attack. For other attacks, please refer to our paper for more details. Future AR platforms might be fully multi-application or multi-user, which makes this problem even more serious. Similar to what we learned from previous work on the platforms, on the browsers and the OS or the Windows system, we hope to provide concrete suggestions on how we mitigate these issues. So based on our finding, we provide 2 sets of recommendation. First, we identify how known defensive strategies can be applied to resolve some of these issues. For example, techniques like improved provenance from the web or Z-fighting mitigation in hope to mitigate some of the 3D object conflicting. Another type is to consider new 3D UI spatial defense, which includes, for example, we know about iframe on the 2D web. How do we design iframe in the 3D environment? Or how do we design API that prevent third-party application from overlaying 3D content on our target object? And finally, our framework can extend to future AR applications, as we have already demonstrated or had some preliminary results for Apple Vision Pro once we get a device early this year. We hope our framework can also help future researchers to evaluate a new device. For example, the AR headsets that Google, Samsung, and Qualcomm are currently working on. To summarize, we present an empirical analysis of 5 different AR platforms, systematically investigate how they handle the 3 AR UI security properties we identified. We demonstrate 5 proof of concept attacks and found that all platforms, including Apple's ARKit, Google's ARCore, Meta's Oculus, Microsoft HoloLens, and WebXR, are all designed and implemented in the ways that enable our AR UI attack to succeed. Along with this paper, we open source our code and the video demonstration for this attack. Thank you. I am happy to take any questions.